Hello, students. Today, we're going to tackle a really interesting and important topic in your chemistry syllabus, displacement reactions and the reactivity series. Now, this is key to understanding why some metals are, well, very eager to react, while others are a bit more, shall we say, lazy. So, let's begin.
Just think about this for a moment. Why is it that an iron gate in your neighborhood gets all rusty over time, but the gold jewelry, maybe a ring or some earrings your mother wears, stays perfectly shiny year after year? One metal changes completely, while the other seems to last forever. The answer to this why is all about the chemistry of these metals.
Now, to really get to the bottom of this, we need to remember something we've already learned. You might recall us talking about metal reactivity. The main idea, if you remember, is that not all metals behave in the same way. Some are extremely reactive, while others are very, very unreactive.
Think back to when we discussed how metals react with water. Just imagine sodium, a tiny, tiny piece. When you drop it in cold water, poof, it zips around and catches fire. A very violent reaction. But then, think about copper. You can put a copper wire in cold water, you can boil the water, you can even pass steam over it, and what happens? Absolutely nothing. This simple comparison shows us just how different their reactivities are.
So, this big difference in reactivity, it makes you wonder, doesn't it? What happens if we put these metals in a kind of competition? For instance, what if a very reactive metal comes into contact with a solution that has a less reactive metal in it?
Well, that's exactly what leads us to something called a displacement reaction. It's a great name because it's exactly what it sounds like. Think of it like this. A stronger, more reactive metal comes along and pushes a weaker, less reactive metal right out of its spot in a compound.
Okay, so to really see this happen, let's do a little thought experiment. Imagine we are right here in the lab. I'm going to take a regular iron nail, and over here I have a test tube filled with a bright blue liquid. This is copper sulfate solution. Now, all we're going to do is drop the iron nail into this blue solution and we'll just wait, maybe for about 20 minutes, and let's see what happens.
So while our experiment is running, let's quickly go over the official definition. A displacement reaction is a chemical reaction where a more reactive metal displaces or pushes out a less reactive metal from its salt solution. It's really that simple. The more powerful metal just takes the place of the weaker one.
All right, our 20 minutes are up. Let's look at our test tube. What do we see? Two very interesting changes. First, look at the solution. That bright blue color? It's fading away. It's becoming a pale light green color. Why? Because the iron, which is more reactive, has pushed the copper out and formed iron sulfate. And the second change? Look very closely at the part of the nail that was in the solution. You see that reddish-brown coating? What do you think that is? That is pure copper metal. It has been kicked out of the solution and has now coated the iron nail.
Now let's write down what just happened in the language of chemistry. We started with solid iron, Fe, S, and it reacted with aqueous copper sulfate, CuSO4, AQ. And what did we get? Well, the iron pushed the copper out, so now we have aqueous iron sulfate, FeSO4, AQ, and solid copper, CuS. See? The iron has literally just swapped places with the copper.
Okay, now it's your turn to think like a scientist. We just saw that iron can displace copper. So here's a question for you. What do you think would happen if we tried it the other way around? What if we took a piece of copper wire and put it into an iron sulfate solution? Just take a moment and predict the outcome.
Did you guess that nothing would happen? If you did, you are spot on, absolutely correct. And why? Because copper is less reactive than iron. It's not strong enough to push the iron out of its place, so no reaction. This is very important. It tells us that these reactions aren't random, they follow a rule. And the rule is all about which metal is more reactive.
Okay, so this raises a very practical question, right? How are we supposed to know which metal is more reactive than another? Do we have to do an experiment every single time? Well, thankfully, no. Chemists have already done the hard work for us and created a very, very useful tool. It's called the reactivity series, and it's basically our guide for predicting all of these reactions.
So, what is this reactivity series? It's really just a list of metals, all arranged very neatly in order of how reactive they are from top to bottom. At the very top, you have the most reactive ones: potassium, sodium. These are the ones that react violently. Then, as you go down the list, through calcium, magnesium, aluminum, the reactivity starts to decrease. You see zinc, then iron,
And way down at the bottom, that's where you find the least reactive metals, silver, and right at the end, gold. And this brings us back to our first question, doesn't it? This is why gold jewelry stays so shiny. It's just not interested in reacting.
Now, you might be looking at this list and thinking, wait a minute, hydrogen isn't a metal, so why is it sitting here in the middle of our list? Well, that's a very good question. Hydrogen is here because it acts as a very important benchmark, a kind of dividing line. The rule is simple. Any metal that is above hydrogen in this series is reactive enough to displace hydrogen gas from dilute acids, but any metal that is below hydrogen, like copper, silver, or gold, they are not reactive enough to do that.
Okay, so this series is great for the lab, and it will definitely help you in your exams. But you might be wondering, does this matter in the real world? And the answer is a big yes. This isn't just theory. The reactivity series has huge practical uses that affect our everyday lives.
Take, for example, getting metals out of the ground from their ores. This is called metallurgy. Well, the reactivity series is like the instruction manual for this. For the really reactive metals at the top of the list, like sodium or aluminium, they hold on so tightly to their compounds that you need a very powerful electrical process called electrolysis to break them apart. But for the metals in the middle, like iron and zinc, they're less reactive, so we can use a simpler method, like heating them with carbon.
And let's go back to our rusty iron gate. The reactivity series gives us a clever way to stop that from happening. It's a process called galvanization. What we do is coat the iron with a thin layer of zinc. Now, look at the series. Where is zinc? It's above iron. That means zinc is more reactive. So if that coated iron gets scratched, the air and water will react with the zinc first. The zinc corrodes, but the iron underneath is safe. We say the zinc acts as a sacrificial layer. Very clever, isn't it?
Okay, now let's talk about exams, because I want you all to do well. There are a few common mistakes that students often make with this topic, so let's avoid them. First mistake, writing a reaction that can't happen. For example, writing that copper reacts with iron sulfate. We know that's wrong because copper is less reactive. Second mistake, forgetting about our hydrogen benchmark. Remember, metals below hydrogen will not give you hydrogen gas with acids. And the third common issue is just mixing up the order of the metals. So please take some time to learn this series, especially the order of common metals like zinc, iron, and copper.
Okay, we've covered a good amount of ground today, and you've all followed along wonderfully. So before we wrap up, let's just quickly recap the main points.
So, 3 things to remember from today. Number 1, a more reactive metal can kick out or displace a less reactive metal from its salt solution. That's the main rule. Number 2, the reactivity series is our master list that tells us which metal is more reactive. And finally, number 3, we use this series to predict if a reaction is possible or not. So, we've understood the what of these reactions. We know what happens, and we know which metals are more reactive. But there's a deeper question, isn't there? Why? Why is potassium so reactive? Why is gold so unreactive? What's happening at the level of the atoms? Well, the answer to that why has everything to do with electrons. And that is a story for our next class. Thank you for listening.